So in this first lecture, we will be discussing about the concept of compound pendulum and we will derive an expression for time period t of a compound pendulum. Now there is an alternate name for compound pendulum. It is also called as a physical pendulum. We should remember this alternate name. Before going to this discussion, we will first try to understand the concept of a simple pendulum, which we are already familiar with. We all know that simple pendulum is in the form of a rigid heavy bob suspended by a long inextensible string of length L, which is attached to a rigid support. In this type of system is usually called as a simple pendulum, and we all know that time period t for this system is twice pi under root L by G. We have already performed experiments related to such simple pendulum case. Now the problem with this system or this formula is that this type of system is not the only case which can oscillate or which is able to oscillate. There are other structures, like we can have a triangular shaped body, we can have a rectangular shaped body, then we can have a circular disc, and all these can be made to oscillate about an axis passing through them. So all these bodies are capable of oscillating. Now if we try to measure the time period t of such bodies, we cannot apply the previous formula which was derived for the case of simple pendulum. Now we must be able to measure the time period of a body of any random shape or size, and we must be able to verify the measured time period with a theoretically determined quantity. So there must be a general formula for the time period of a rigid body of any shape. So there is no restriction at all on the shape of the body. The only condition is that the body should be rigid. The next thing is that the body oscillates in a vertical plane. So body oscillates due to gravity. And the last thing is that it should oscillate about an axis passing through it. So informally we have now defined what do we mean by a compound pendulum. So compound pendulum is a rigid body of any shape which is able to oscillate in a vertical plane under the action of gravity about an axis passing through it. So yes, that is the definition of a physical pendulum. Now for that we must also be familiar with another concept called moment of inertia. So this is a basic definition which we must already know. Suppose there is an axis, we call this as axis of rotation. Suppose there is a point mass m which is rotating about this axis by keeping a distance r from the axis of rotation. Then we define the moment of inertia of this mass by letter I as mr squared. So this is the case for a single particle. Now suppose there are n number of such particles, m1, m2, m3 and so on, at distances r1, r2, r3, r4 and so on. Then the moment of inertia will be just the summation of mi ri squared over all I. So we just add up the moments of inertia of the all particles. In reality, the body is made up of n number of such large particles. So we get a continuous distribution of mass. So when we replace a discrete function by a continuous function, the summation is replaced by an integration and the similar formula is applied. Okay, so using a formula which involves integration, we can have the moments of inertia I of any bodies. Just for an example, we know that moment of inertia of a disk about an axis passing through its center is just mr squared, where m is its mass and r is its radius. Similarly, the moment of inertia of a sphere, this one was for a disk, now this is for a sphere, is 2 by 5 mr squared. So we have already learned all these formulae. Now why are we discussing this? Because all these bodies are rigid and they are able to oscillate. And since all these bodies are having different shapes and sizes, their time periods are going to differ and they will mostly depend upon the moment of inertia of the structures. Now, for the discussion, we will take a body of random shape. So there is no restriction on the shape and size of the body. So we will be considering a body of any random shape, and we are going to assume that this point G will be the center of gravity of this body. Now suppose there is a point O in the body about which the body is able to oscillate. So this will be called as axis of oscillation, and this point O will be called as point of suspension, just because the body is suspended about the point O. Now we can draw a line joining these 2 points and call the distance between them to be small l. Now we can push this body a little bit so that it gets displaced from its equilibrium position. So initially the body was like this. Initially the body was like this, Just a minute. And this was the equilibrium position, and since it is now displaced, this axis will be slightly tilted, say through an angle theta. This is L. This will be the new position of point G, which is the center of gravity. This is L. And now we will be discussing about the forces acting on this. So essentially we are going to apply Newton's law. But remember, this is rotational motion or oscillatory motion. So in this case, this is the equilibrium position, this is the displaced position, and suppose m is the mass of this body. Now we suppose that all the force applied on the body acts on this point G, which is the center of gravity. So simply the gravitational force acting will be mg. Now this force can be resolved along two components. If this is theta, then similarly this will be theta, and this component will be just mg cos theta, and the other component will be mg sin theta. Now just focus on this component. Since this is directed towards the left, this mg sin theta component is responsible for bringing the pendulum back to its equilibrium position. Now this force, or this component of force, applies a torque on the body. Torque is defined as R cross F. What is R? If this is the axis of rotation, this is the point at which the force is applied. Suppose this is F bar. Then this distance between the point and this axis is R bar, and we define torque as R cross F. So now in this case, this is the point O, this is point G, and this distance is L. So in our case, the torque is going to be, we will discuss only the magnitude part, tau equal to R, which is in our case L, and force, which is in our case mg sin theta. So we will restrict ourselves for small angular displacements. So theta is small, and in such an approximation we know that sin theta is approximately theta when theta is expressed in radians. So this equation reduces to just Lmg theta, since we are saying that theta is small enough. Now one more thing we have to add, because we have considered only the magnitude. If we include the direction, we must remember that this torque is the restoring torque, in the sense that it tries to restore the position of the body to its equilibrium position. So restoring torque is usually represented by a negative sign. Now this will be our first important equation. Now we know that by definition torque is I times alpha. I is already discussed, it is the moment of inertia of the body. Alpha is angular acceleration. So we all know that alpha is just rate of change of angular velocity, and omega, which is the angular velocity, is rate of change of angular displacement. So alpha will be second order derivative of theta. If we combine these two equations, we will directly get this result. As a result, the torque will be I times d2 theta by dt squared. This is the second important equation. Now, the left hand sides of equation 1 and equation 2 are the same, that is the torque. So we can equate the right hand sides as well, which gives us I d2 theta by dt squared equal to minus mgl theta. So this can be rearranged to get d2 theta by dt squared plus mgl upon I into theta equal to 0. All the terms in the bracket are just constants for a given body. G is the acceleration due to gravity, m is the mass of the body, L is the length between point O and point G, and I is the moment of inertia of the body. So just call that constant as some omega squared. So this is our substitution, that omega squared is mgl upon I. So this makes this equation d2 theta by dt squared plus omega square theta is equal to 0. Now this equation of motion can be solved, and this is the equation of a simple harmonic motion. So an object performing simple harmonic motion. Okay, but we are more interested in an expression for time period. So we know that omega is angular frequency, which is 2 pi n or 2 pi by t. So omega squared would be 4 pi squared by t squared, which is also equal to mgl upon I. We can just refer back to the previous equation. So this can be rearranged to get t squared equal to 4 pi squared I upon mgl, or t equal to twice pi under root I upon mgl. So this is a more general formula, which is nothing but the time period of a compound pendulum. Now we can check whether we come across the formula for simple pendulum using this. The structure for simple pendulum was already discussed. This is L, this is M. So in this case, the moment of inertia would be just m times L squared. Now if we substitute this in our equation, t becomes 2 pi under root ml squared upon mgl, which is twice pi under root L by G, which is well known previously. So we know that even the formula for simple pendulum could be derived from the more fundamental formula of time period for a compound pendulum or a physical pendulum. Or in other words, simple pendulum is just a special case of compound pendulum. Okay, thank you.